Welcome to the first lecture of the course CS 6003, the probabilistic method. Right. So usually in a course we start by giving what is an overview of the course, right? So ideally I should have started by telling you what is the probabilistic method, what is it, how is it used, where is it more powerful, and so on. But I feel that it will be better appreciated, such an overview or an introduction would be better appreciated after we have seen at least a few examples. Okay? So it's difficult to capture the idea of the probabilistic method in one or two sentences unless you see how it is used in some examples. Yeah, so instead of, so this course overview I will do, but I'll do it maybe after a couple of lectures, but we'll begin with some examples, right? At least we'll see two quick examples and then a long one. Maybe the long one we will push to the next class, next lecture based on how long this recording goes, okay? So the first example where you will see this probabilistic method applied, the one I have picked is called the bipartite subgraph problem. So the question is given a graph which is, by the way, I'm kind of assuming that you know the definition of graph, bipartite graph, and so on, right? Even if you don't know, if you kind of don't remember it, you can go and quickly refresh those things. These are not any difficult definitions. If there are definitions which are difficult to grasp, then I'll spend more time on that, right? So a bipartite graph is a kind of a graph which does not have any odd cycles. That's one way to define it. Equivalently, it can also be defined as a graph in which you can do a proper vertex coloring using two colors. Thirdly, again, third equivalent definition would be the vertex set of this graph can be partitioned into two independent sets. Independent sets are sets of vertices which do not have any edges between them. So a bipartite graph is one in which you can partition the vertex set into two independent sets. Okay, this means all the edges are actually crossing these two independent sets. So this is a partition of the vertex set, and this is probably the original definition of bipartite graph, and that's why the name is bipartite. If it was the second condition, then it would have been called a two colorable graph. And if it was the first definition, absence of odd cycles, it could have been called an odd cycle free graph, right? So it's usually in a first course in graph theory, you learn that all these three definitions are the same. What's the problem that we are considering? We are given a general graph which most of the times will not be bipartite, and we want to find a large bipartite subgraph contained inside it. So what's a subgraph? A graph is a subgraph of another graph if you can obtain the smaller graph by deleting edges and vertices of the old graph. Okay, so that's what a subgraph is. So we want as large a subgraph as possible of the given graph, where large is quantified in terms of number of edges. Okay, and the theorem here states that if the given graph has m edges, then you can always find a bipartite subgraph with at least half of that many edges, okay, with at least m over 2 edges. This fact can be proved in multiple ways. The intention here, the aim here is to show how you can prove it using a probabilistic method. Okay, so first, as a thought experiment, consider this process. Okay, so we are going to color each vertex. Okay, mind you, our objective is on the number of edges, but still the coloring that we are speaking about is a vertex coloring, and we don't insist that it is a proper vertex coloring in the sense that adjacent vertices get different colors. In fact, we are going to pick every vertex, toss a coin, a fair coin, which means with probability half it will come head and probability half it will come tail. If it comes head, let's say we are giving it color 1, red, okay, and if it's tail, then we are giving it color 2, let's say blue. Okay, and that's all. And each of these vertices, this process is repeated independently. Okay, so each vertex of G is color each vertex of G, actually I should say independently and uniformly at random. Okay, so independently and uniformly at random with two different colors. Now what do? Now I delete all the monochromatic edges. Okay, that is edges whose both endpoints have the same color, edges between two red vertices and between two green vertices. These are deleted. So what are surviving? The surviving edges have the endpoints with different colors, right? Now it should be clear that once you do that, the surviving edges, if you put them, consider them as a graph, that is a bipartite graph. Why? You can think of either the second definition or the third definition of a bipartite graph that we gave, right? Because once you have deleted all the monochromatic edges, all the remaining edges under this two coloring are now proper, right? Because the endpoints of any edge, any remaining edge, any surviving edge, any edge in H, okay, are of different colors. So this two coloring, this random two coloring, after you have deleted all the edges for the graph H is a proper coloring. So it fits the second definition of a bipartite graph. It is such, right? The third definition can also be similarly verified. All the vertices which get the red color form one part, and all the vertices which get the blue color under this random coloring, they form the second part. Since we have already cleared all those edges within parts, those are now independent sets, and hence it fits the definition of a bipartite graph properly. Okay, so this way we get a bipartite subgraph H, but that's not the end of it, right? We want to get a bipartite subgraph with at least m over 2 edges. But now what would be the number of edges in H? That would be decided by luck, right? Because it's a random experiment. After all, there may be on a lucky day, a lot of edges may survive, and on an unlucky day, maybe, in an extreme case, it is possible with a very, very small probability that all the vertices are actually colored red. Okay. In fact, it happens with a probability half to the power n, where n is the number of vertices in the graph. So in that case, you will end up with a bipartite graph, which is essentially the empty graph with 0 edges. Okay, so the worst case is really frightening, but our theorem only says there is one bipartite subgraph which is very large in terms of number of edges. So maybe the worst cases are there, but still the good case or the best case may be to our advantage. But how do we really show that? Okay, so here is where we continue our probabilistic analysis, right? Already step 1 is a probabilistic step, okay, because you are doing a coloring in a random fashion. You are coloring it independently and uniformly at random. Now let us analyze the expected number of edges that will survive, okay, in this kind of a coloring. So in order to find this expected number of edges that will survive, we do a two-step analysis. Firstly, we observe that each edge in G, the given graph G, survives with a probability of half. Why is that true? Maybe you should, rather than listening to my next sentence where I say why is it half, you should rather pause the video and convince yourself that this is half. Okay, assuming that, by the way, this would be in my opinion, this would be the one good way of being very engaged with while you are following a recorded lecture, right? Whenever I ask a question, even if I don't explicitly say please pause and think, it may be a good idea to pause and think and see if you can figure it out yourself. If you figure it out yourself, you are more likely to remember it for sure, and also you will have a deeper understanding of it. Okay, but anyway, this question does not fit that kind of a hype. The probability is half because there are 4 possibilities for each edge, right? 4 possibilities for the colors of the endpoints of each edge. It could be red green, red blue, blue red, or blue blue. Under 2 of these cases, the edges get deleted. The other 2, the edge survives. All these cases are equally likely because of the independent uniformly at random coloring. All these 4 events have probability 1/4 each. Since 2 of them are favorable, the answer is half. Okay, so this is our first observation. Each edge survives with a probability half. So if each edge survives with a probability half, then we see that the expected number of edges that will survive is m by 2. Okay, now intuitively this is a very believable argument. You can make it rigorous. Okay, by the way, the survival of two different edges are not necessarily independent events. Okay, for example, if the two edges share a vertex, right, then it may be possible that there is a dependence. But when you are counting the expected number of edges that survive, it really does not matter whether they are independent, these events are independent or not. Don't worry if this is a slightly confusing bit, but later we will study it more slowly and more carefully, and you will see that expectation is a linear operator, and expectation of the sum of two random variables, e of x1 plus x2, will turn out to be the sum of their expectations, e of x1 plus e of x2, irrespective of whether x1 and x2 are independent or not. Okay, so this is the rigorous justification of why the expected number of edges that survive is m by 2. But in the first lecture, it is enough if you understand it intuitively. Okay, now next comes probably the more surprising kind of argument, right? Now, if the expectation of some random variable, the random variable that we are talking here, let's say the random variable that we are talking here, x is actually the number of edges that survive. So it's a number, okay, and the expectation of that number is m by 2. That's what we have said, right? We have said that expectation of x is m by 2, right? Yeah. So this is what we have. Okay, that is a bad color choice, sorry. But anyway, yeah, the expected number of edges that survive is m by 2. Now, from that, it follows that there is at least one coloring in which m by 2 edges survive. Okay, so think about what an average is, right? So expectation is in some sense an average, just that it's kind of a weighted average depending on the probability of each value of x, right? So this is usually, this x in the range of x, probability of x times x, right? So this is a weighted average. But weighted or not, if the average of certain quantities is some mu, then surely in that collection there exists at least one, in the range there exists one value which is greater than or equal to average. I cannot always say there is something which is strictly greater than the average, because in one scenario everything may be at the average, right? Easy examples to get this intuition clear would be things like the class average in a test, right? So let's say I conduct a test out of 100 marks and I tell you that the class average is 75. Then you can be sure that at least one student got 75 or more. Okay, and this is true even if it's a weighted average, right? And I will get, by the way, when I take a weighted average, let's assume that I can further say that this would be true for one student whose weight was non-zero. That his marks in the test would be at least class average, right? By the way, I can also say there will be one student whose test score is at most the class average. Both of these statements are very easy to prove, right? Because if everybody had more than the average, then you can easily see that the average would be more than the average, which is a contradiction. Same thing applies if everybody's score was less than the average, right? Each of these cases leads to easy contradictions, and hence this conclusion, right? So that's what we are using. There exists at least one coloring. Since the average or the expectation is m over 2, there is at least one coloring among the 2 raised to n possible colorings, right, in which at least m by 2 edges survive. Okay, and that's what we need, right? I mean, then this coloring and the bipartite graph H, which is obtained by deleting the monochrome edges in this coloring, that will give the required bipartite graph, right? Because this bipartite graph has at least m by 2 edges. Okay. Yeah, so this is the proof. Okay, this proves the theorem that any graph with m edges has a bipartite subgraph with at least m by 2 edges. Okay. Now this calls for a lot of remarks, right? Suddenly, the first thing to notice here is that the statement of the theorem is a very, very deterministic statement. Okay, it's not saying that with very high probability graph with m edges has a bipartite subgraph with m by 2 edges. No, it's saying that always any graph with m edges has a bipartite subgraph with at least m over 2 edges. Okay, so the statement has no uncertainty to it, but the proof used randomness. Okay, and another point, remark number 1. Remark number 2, this, if you can we convert this proof into an algorithm? Okay, yes, we can, because instead of picking because for the final statement here says that in one of the colorings, right, after you delete the monochromatic edges, you are left with a bipartite graph with at least m by 2 edges, right? Which means if you can search through all the possible colorings, you will find this graph. Okay, but the only issue is that it is an algorithm for sure. You can convert it into an algorithm, but it's an exponential algorithm. Okay, the brute force way of converting this proof into an algorithm will involve searching through 2 raised to n different colorings. Hence, it is and not an efficient algorithm. It's not a polynomial time algorithm. But for this problem, actually, there are very cute polynomial time, I think even linear time algorithms to find this graph with m by 2 edges, but that's not our topic, at least in the first lecture. But I want to say that, okay, though there is a randomness involved in the proof, this leads to a deterministic algorithm by going through all possible colorings, but a very inefficient deterministic algorithm. Okay, then yeah, and then the third remark that I wanted to make this is here, this, yeah, or maybe it's like too early to say about this linearity of expectation. I have anyway hinted that before. Okay, so yeah, so let's but okay, but there is a fourth remark which I anyway wanted to say, and that is, here, if you think of this as a search problem, what do I mean as a search problem? You know that there is this bipartite graph, and you are trying to kind of, or that this one of these colorings generate a bipartite graph with a large number of edges, and you are trying to search for that coloring. Okay, and somehow what the magic that is happening here is that if you guess that coloring randomly, okay, by doing this very natural random experiment of coloring each vertex independently and uniformly at random, right, then it looks like there is a good chance that it gives such a coloring. Okay, this is again not a justified statement, because we did not really calculate the probability that a random such coloring, what is the probability that if you just do this this process using coin tosses, what is the probability that you will end up with a graph with m by 2 edges? Okay, so yeah, you can analyze that probability. It's going to be a significant value, but if you are ready to live with something like m by 2 minus a small factor, then with very high probability one can show that this random coloring will achieve something with a bipartite subgraph with m by 2 minus something like order of root m edges. Okay, but that requires a more tighter concentration inequality kind of analysis. Okay, now we can also, since there seem to be a lot of luck involved with this proof, it's natural to ask, is there a better bound? Can we do better than m by 2? Is it guaranteed that every graph on m edges has bipartite subgraph with significantly larger than m over 2 edges? Okay, answer is no. I mean, this is almost tight. I mean, maybe there would be some round of corrections here and there, but other than that, you can see that this is tight by looking at the complete graphs. Okay, so if you take a complete graph on n vertices, what is the starting number of edges? M is equal to n choose 2. So if you again ignore that rounding, it is n into n minus 1 over 2, but approximately it is n squared over 2. And what is the largest bipartite subgraph inside Kn? You can verify that like any bipartite subgraph is of the form k some let's say k some little k and n minus k, right? You take your complete graph and put k vertices on one side, n minus k vertices on one side, and then retain all the edges which cross the partition, delete all the edges within a partition, and you can see that the number of edges in this case is k times n minus k. And now you try to maximize it, like which value of k does this maximize? You will find that you can either do a differentiation and set it equal to 0, or you can use the arithmetic mean, geometric mean inequality or whatever, and see that an equal split where k equal to n by 2 gives you the split where the bipartite graph has maximum number of edges. So the largest bipartite subgraph of Kn turns out to be the complete bipartite graph with n by 2 floor vertices on one side and n by 2 seal vertices on the other side. This also has what is the approximate number of edges here? It's this times this, which is approximately n squared over 4. See that this is approximately m by 2. Okay, so yeah, so this m by 2 is not far from tight, right? I mean, so our probabilistic method in the first example that we see in this course is quite it's quite tight also. Okay, so I hope you have understood this problem. Otherwise, always pause and go back and see that every step was convincing, especially these steps here where we started introducing the probabilistic method for the first time. Okay, so assuming that it's clear, let me move on to a second example, slightly more complicated than that, but still a very manageable example. Okay, but for this I need to define what is an antichain. So an antichain is a family of sets with an extra property. Okay, so we are not talking about a single set here. We are talking about a family or a collection of sets, which I denote by this script f. But when do I call a collection of sets an antichain? I call a collection of sets an antichain if no member of this family is properly contained inside another. Okay, like if I take the same member twice, then by definition one is contained in the other, but still not properly contained in other. Okay, so that's what an antichain is. So there does not exist two sets S and T in the family such that S is a proper subset of T. Very easy to construct examples, right? So if you look at this example here, 1, 2, 1, 3, 1, 4, 1, 5, etc., all the way up to 100, you see that no set is in this family is a subset of another. So this is an antichain. Similarly here, if you take this 1, then you see 2, 3, 4, but here it is 2, 3, 5 and 6, right? 3, 5, 6, 7, 8. You can verify that. Unless I have made some careless mistake, this is also an antichain. I put this example just to illustrate that not all sets in an antichain have to be of the same size. Okay. Now, a very nice way to construct an antichain is to take a ground set of 1 to n. Okay. By the way, I hope this notation is familiar to you. This notation here means the numbers 1, 2 all the way up to n. Okay. So you take all the subsets of n which are of size k for some k in the valid range. Okay, so these are all k-sized subsets of n. I claim that that's an antichain, right? Why? Because if two sets are of the same size, one cannot be a proper subset of the other. So this relation is easily verified. Okay, so these are some examples of antichains. Okay, so I hope the definition of an antichain is clear, and the theorem that we are going to state next is about largest anti-chains, which means not that any particular set in the family is large. We are trying to have the size of the family to be large. Okay, we want to include as many sets in this collection as possible. Okay, but I mean, if you just say that you want a anti-chain with a very large number of sets, it's very easy. You can kind of extend this example here to any number you want. Okay, so that's not an interesting question. The interesting question is when you limit your ground set. Ground set is in some sense the union of all the sets in the family. It's the universe from which each set in the family picks its members. Okay, so the theorem is about what is, once you fix the number of elements in the ground set as some little n, let's say, what is the largest anti-chain that you can now form out of this universal set. Okay, so this is a very famous theorem and it's named after a mathematician called Sperner. It's quite an old one, 1928. So this says that if F is a family of subsets of this universal set 1 to n, okay, so your ground set has n elements and this family forms an anti-chain, then this anti-chain, the number of sets in the family is at most n choose n over 2 floor. Okay, this is what this theorem says. Okay, by the way, you can see that this example is tight. Okay, I'll skip the proof. And why is this example tight? If you choose all the n by 2 sized subsets, okay, this is something which we have just seen in our third example of an anti-chain. If you choose all the n by 2 floor sized subsets of 1 to n, then we saw that it's already an anti-chain. And in this case, what is the size of F? Here, the size of F will be, or the number of such sets that you can choose will be n choose k, where k is the floor of n by 2. Okay, so this result is also tight. Okay, and we are going to prove this using probabilistic method again. Okay, so just to give a name to each of the set in the family, let's say there are m sets in the family, and I label them as S1, S2 all the way up to Sn. Remember that each of these Si is a subset of 1 to n. Okay, now this is the the coin tossing part. Okay, so yeah, you toss the coin here, right? And but this time you cannot kind of do it with a single coin toss. We are going to pick a permutation of numbers 1 to n uniformly at random. Okay, what does uniformly at random here mean? You know that there are n factorial different permutations possible for numbers 1 to n. So when you say you pick a permutation uniformly at random, you mean you assign a probability distribution which gives probability 1 over n factorial for each of the permutations, and according to this distribution you pick a permutation. Okay, this can also be done in a step-by-step fashion. It's like the first element in the permutation could be any of the n guys chosen with probability 1 by n, and the next element in the permutation, sigma 2, would be any of the remaining n minus 1 guys chosen uniformly at random. So each of them will have probability 1 by n minus 1, and so on. The third guy is chosen to be any of the n minus 2 remaining guys, right? And if you evaluate, you will again get 1 over n factorial as the probability of picking that thing. Okay, so here also you can construct this or you can do this sampling of a permutation uniformly at random by n repeated random experiments done like this, and each choice in some sense is independent, but again it's not really independent. No, how do I say? There is some dependency in the sense that if you pick somebody here, then you don't pick them again. So that dependency is there, but among those who are surviving, this is a uniformly at random choice. Okay, so this is the random experiment. Okay, now what is the event whose probability I want to analyze? This is the event. Okay, the event EI that I want to analyze. Okay, the event EI that I want to analyze is the event that the elements of Si appear as a prefix of sigma. Okay, so I am looking at the event where Si appears as a prefix of sigma. What does that mean? So if you write out this sigma as sigma 1, sigma 2, sigma 3 all the way up to some sigma n, then exactly you go to some sigma k, this will exactly be equal to Si. Okay, that's what you mean by saying that the elements of Si appear as a prefix of sigma. No, they appear as the first cardinality Si elements of sigma. Okay, so this is the event whose probability that I want to analyze. Okay, so suppose you have your size of Si to be k. If your size of Si is equal to k, then can you pause and think what will be the probability that if you pick a random permutation sigma of n, Si will appear as a prefix of sigma. Okay, I'm assuming you have thought through, because the total number of permutations you have is n factorial, that's the denominator, out of which in how many permutations do you have Si as the prefix? So this essentially means you can permute these guys in any way you want. These Si guys would occupy the first k positions, but you can permute them in whichever way you want, which is k factorial. And these remaining guys, again you can permute in whichever way you want. So that will give you an n minus k factorial. Okay. Now let us again, by that same trick that we used earlier. Okay, by the way, if you have noticed, this is 1 over n choose k, right? And I actually want a lower bound for this probability, which means I want an upper bound for n choose k, right? But we know that the maximum value that n choose k attains is when k is equal to n by 2 floor or seal. Okay, when it's n is an odd number, these are two, n by 2 floor and n by 2 seal are different, but n choose n by 2 floor is same as n choose n by 2 seal. Okay, so since this lower bound is there, I can say that this is at most, this is at least 1 by this, right? So this is important. Okay, so this relation we will keep in mind, that probability of Ei is lower bounded by the reciprocal of n choose n by 2. Okay, but now notice that E1, E2, E3, etc. are pairwise disjoint events. What does that mean? Or they are mutually exclusive events. What does that mean? I'm saying that if S1 and S2 are two different sets, and if S1 is the prefix, then S2 cannot be the prefix. Why? Again, pause and justify. This is the interesting part. If you find this out yourself, you will be happy, right? I'm saying that when an event Ei occurs, Ej will never occur if I not equal to j. Or equivalently, I'm saying that if some Si occurs as a prefix, then a different Sj will not occur as a prefix. Why? Because maybe the next prefix is either larger or smaller. Let's say it is smaller. But if this is smaller, then that means Sj is a subset of Si, a proper subset of Si, which violates the anti-chain property. And if Sj was larger, if it was a longer prefix, then Si is a subset of Sj, which also violates the anti-chain property. Okay, so the events E1 to Em are pairwise disjoint or pairwise exclusive, pairwise mutually exclusive. Why? Because S1 to Sm is an anti-chain. This is where we are really using the fact that it is a anti-chain, right? Okay, so this is the second observation. We have a lower bound on probability of Ei and for each I, and we also have this observation that E1 to Em are pairwise disjoint. Okay, and what do we get when events are pairwise disjoint? Then probability of their union is equal to sum of their probabilities. Okay, so in general, you could have only put a bound like this, and this is called the union bound. Probability of the union of collection of events is upper bounded by sum of the probabilities of the individual events. This would have been the union bound. Okay, but this is not what we are saying here. We are saying here something which is much stronger, that this is an equality because of this pairwise disjointness or mutual independence. We can say that you get a equality here. Okay, this is a basic fact in probability. You can verify it using Venn diagrams even. Okay, so now we know we have a lower bound for each of these guys, right? This is lower bounded by n over n choose 2 floors reciprocal. The same thing, this is also lower bounded by this, right? So the sum of all these guys is lower bounded by m times this number, okay? M times this lower bound for each of them, okay? So each of them is lower bounded by this, so sum of all of them is lower bounded by m times the same quantity, right? And now I substitute this equality. This sum of these probabilities are nothing but probability of their union, but since it is probability of some event, it is at most 1. Okay, so now if you put it together, it looks like again suddenly out of the blue that m would be less than or equal to n times n by 2. And this is Sperner's theorem, right? Because what is m? M is the number of sets in the family. This is the size of the antichain, and this is what Sperner's theorem anyway intended, stated, right? It stated that it is at most n choose n by 2. Okay, and yeah, this also I mentioned that this turns out to be tight. Okay, again I think all the some of the earlier remarks at least apply, but here there is an added, this proof I will consider it as to be surely one order of magnitude tougher than example 1. Okay, this example 1 is something which you can give it as an exercise problem or even a, how do you say, an assignment problem, or in a special case even an exam problem. Okay, because the construction of this subgraph is in some sense direct. Okay, once you are familiar with a probabilistic approach, okay, you are trying to see, okay, you know that you have to construct a bipartite subgraph. Okay, let us do it this way. But here somehow this step, okay, picking a permutation right uniformly at random, this step seems to have come out of the blue. It seems to have come out of nowhere. Okay, so in that sense there is a kind of a magic value about this step, right? So that's why I consider this proof a bit more demanding. Okay, by the way, the original proof by Sperner did not use the probabilistic method. He used a different proof, but this is from 1928, whereas probabilistic method started getting applied widely from 1940s after Erdős and so on. Okay, so and yeah, the first remark again applies. The statement is an entirely deterministic statement. There is nothing uncertain about the statement. It does not say that with very high probability or significant probability something happens. It says that for any family which is an antichain, this upper bound holds. Okay, so this is going to be a recurring theme. Okay, when the probabilistic method, only the method has the probability aspect to it. Okay, the result that you get by applying this method often turns out to be a state or a fact which has no uncertainty to it. Okay, it would be a deterministic fact. That's in some sense what is very cute about this probabilistic method. Okay, so yeah, with that we will wind up this lecture. The third example that I have, the third example we will on some free sets we will do in lecture 2. Okay, but make sure that you understand especially the example 1 very carefully, because this also uses in the last stage idea that is very similar to the example 1. Thank you.